Hi class, good day. Alam nyo, ang bilis ng panahon, dati prelim pa lang tayo, tapos midterm, at ngayon, finals na. You've learned so much already, from the foundations to the more complex pharmacy concepts. Now, this last stretch is where everything connects. In this part of our journey, we'll explore deeper, applying what you've learned in real-world pharmaceutical situations. Think of it as your final rehearsal before stepping into the actual practice of pharmacy. For this last part, we'll dive into Micromeritics, phase equilibria, and chemical kinetics. Micromeritics deals with the science of particle size and surface area, crucial for powder flow, dissolution, and drug absorption. Phase equilibria explains how different phases, solid, liquid, and gas, coexist in balance, helping us understand formulations and stability. And finally, chemical kinetics reveals how fast reactions occur, guiding us in predicting drug shelf life and degradation. Ngayon, pag-usapan muna natin ang micromeritics. Ito ang branch ng science na nag-aaral tungkol sa mga particle properties tulad ng size, shape, surface area, at density. In pharmacy, micromeritics is crucial because the particle size of a drug affects how fast it dissolves, how well it blends in a formulation, and even how effectively it's absorbed by the body. Ngayon, pag-usapan natin ang micromeritics. This field focuses on the study of small particles, the powders and solids that make up many of our pharmaceutical products. Micromeritics examines two main types of particle properties. First, the fundamental properties, which are inherent to every individual particle, like size, shape, density, and volume. Second, the derived properties, which come from combining those fundamentals, such as bulk density, granule volume, and porosity. These properties determine how powders flow, mix, compress, and even how fast a drug dissolves in the body. Let's talk about powder characterization. In simple terms, powders are not just dry solids. They actually contain particles, liquids, and air all mixed together. Their behavior, like how they flow, blend, or compress, depends on many factors: particle size, shape, density, and even how much air is trapped between them. That's why understanding powder characterization is crucial in pharmacy. We analyze both the bulk properties, like powder flow, and the individual particle properties, such as internal and surface structure. Key characteristics include powder flow, which tells us how easily it moves, particle interactions, which show how particles respond to each other, and surface properties, like surface area and porosity, which directly affect dissolution and blending. Let's talk about particle size. This refers to the diameter of individual powder particles, and it's one of the most important factors that affect drug performance. Powders can be classified based on their size. We have coarse particles, larger than 1000 micrometers. These flow easily but dissolve slowly. Then conventional particles, around 50 to 1000 micrometers, commonly used in most tablet formulations. Next, fine particles, ranging from 1 to 50 micrometers, which dissolve faster and are often used in suspensions or inhalation products. We also have very fine particles, 0.1 to 1 micrometer, and ultrafine, smaller than 0.1 micrometer, used for highly specialized formulations like aerosols or nanoparticles. Remember, the smaller the particle, the larger the surface area, and the faster the dissolution. Let's talk about the methods of determining particle size. Alam nyo, hindi pwedeng hula-hula lang ang laki ng particles. It has to be measured accurately because the entire formulation depends on it. There are several ways to do this. First is sieve analysis, the simplest method where powders are passed through a series of sieves to separate them by size. Next is optical microscopy, where we visually observe and measure individual particles under a microscope, perfect for irregularly shaped materials. Then we have the sedimentation method, which determines size, based on how fast particles settle in a liquid, guided by Stokes' law. And lastly, automatic particle counters, which use lasers or electrical sensors to measure thousands of particles instantly with high precision. Each technique gives us valuable insight into how powders behave, whether they flow, mix, or dissolve properly. Let's start with the simplest method, sieve analysis. Ito ang pinakakaraniwang paraan para malaman ang laki ng particles sa isang powder sample. Here's how it works. We prepare a stack of sieves, each with a different mesh number. Mesh number means the number of square openings per linear inch. So as the mesh number increases, the holes get smaller. For example, a 20 mesh sieve has larger openings than a 40 or 80 mesh sieve. We place the largest mesh on top and the smallest at the bottom, then pour the powder sample at the top layer. Next, the whole stack is shaken mechanically for several minutes. Particles are separated according to their size. The big ones stay on top, while smaller particles pass through until they reach a sieve small enough to trap them. The receiver at the bottom collects the finest particles that pass through all sieves. After that, each fraction is weighed, and from these weights, we can calculate the particle size distribution of the sample. Its main disadvantage? Attribution of particles. Some irregularly shaped particles might pass through or get trapped inconsistently. Pero kahit simple, this method is fast, practical, and reliable. Perfect for quality control in solid dosage formulation. As you can see, several sieves are stacked together, starting from the largest mesh at the top, down to the smallest at the bottom, and finally, the pan that collects the finest powder. For example, the 1/2 inch and 3/8 inch sieves hold the bigger granules, while numbered sieves like number 4, number 10, and number 200 capture progressively smaller particles. The 200 sieve has extremely fine openings, meaning only the tiniest particles can pass through. When we pour the powder sample on top and shake the stack, particles separate according to size. The coarse ones stay up, the fine ones go down, and the finest dust-like particles settle in the pan. After sieving, we weigh the material collected on each layer, and from those weights, we determine the percentage distribution of particle sizes. This simple process tells us how uniform our powder really is, whether it will flow smoothly, compress evenly, or cause problems during tablet manufacturing. Now let's look at a more modern and efficient version, the jet sieve analysis. This method determines particle size distribution, just like the traditional sieve analysis, but with one key difference: it uses airflow to separate the particles instead of manual shaking. Here's how it works. The powder sample is poured into the sample feeder, which directs it into a stack of sieves. A vacuum system creates a strong stream of air that passes upward through the sieves. The airflow lifts the finer particles, allowing them to pass through the smaller mesh openings, while the heavier, coarser particles remain on top. At the end of the process, we collect different fractions, coarse, medium, and fine powders, each representing a specific particle size range. This technique is faster, cleaner, and more consistent, especially for dry powders used in pharmaceutical manufacturing. So compared to the old manual sieving, the jet sieve is smarter, combining precision with automation. It saves time, reduces error, and gives pharmacists a clearer view of powder uniformity and quality. Now let's look at a simple example of sieve analysis calculation. Suppose we have 100 grams of powder, and after sieving, the distribution looks like this. 5 grams stayed on the 20 mesh sieve, 15 grams on the 40, 25 grams on the 60 grams on the 60, 35 grams on the 80, and the remaining 20 grams collected in the pan. From here, we can compute the percentage of powder smaller or larger than a specific mesh size. For example, the percent smaller than mesh 40 means all particles that pass through mesh 40, 60, 80, and the pan. So we add them. 25 plus 35 plus 20 divided by 100 times 100%. That's 80%. Next, percent larger than mesh 60 means those that stayed on the upper sieves, 5, 15, and 25. That gives 45%. And lastly, percent smaller than 20 but larger than 80. That's 15 plus 25 plus 35 or 75%. The rule is simple. Smaller mesh number, larger openings, larger mesh number, smaller openings. So this table helps us visualize the particle size distribution, giving us a clear idea of how uniform our powder is for formulation or blending. Now let's move on to optical microscopy measurements. Dito, sinusukat natin ang laki ng mga particles gamit ang microscope para makita kung gaano sila kalaki o kaliit. Kasi yan ay may malaking epekto sa dissolution, flow, mixing at drug absorption. Let's start with ferret's diameter. This is the distance between two tangents on opposite sides of the particle, basically the longest distance across it. Imagine holding an irregular particle between your thumb and index finger, tapos sukatin mo yung pinakamalayong pagitan. That's the ferret's diameter. It tells us the maximum length of the particle. In pharmacy, it helps us check uniformity of particle size in tablet blends. Kasi kung sobrang laki, hindi pantay ang dissolution or sedimentation rate. Next, Martin's diameter. Ito naman yung distance na nagkahati sa particle sa gitna. It represents the average width useful for suspensions and powder flow studies. Kung masyadong iba-iba ang laki ng particles, nagkakaroon ng segregation or poor flow sa formulation. Finally, we have the projected area diameter, the diameter of a circle that has the same area as the projected image of the particle. Parang sinasabi mo, kung ang particle na ito ay isang perpektong bilog, gaano ba kalaki ang bilog? It's important in dissolution and bioavailability studies kasi mas maliit na diameter means faster dissolution, ideal for rapid drug release. So remember, each measurement gives us a different lens to understand particle behavior. Now let's move on to the sedimentation method. This technique measures how fast particles settle or fall through a liquid. We call that the sedimentation rate or free fall velocity. The setup uses the Andreasen apparatus, which you can see on the right. It consists of a sedimentation vessel filled with suspension and a pipette that samples the liquid at a specific depth. Here's how it works. We disperse the powder in a liquid to form a suspension. As time passes, gravity pulls the heavier particles downward, while smaller ones stay suspended longer. At fixed time intervals, we withdraw a small sample using the pipette and analyze how the concentration changes with time. The method follows Stokes' law, which states that the sedimentation rate is directly proportional to the density of the particle, its diameter, and the gravitational pull. In short, the larger and denser the particle, the faster it settles. In pharmacy, this principle is essential when formulating suspensions, emulsions, or injectable products, where uniform particle settling affects stability and dosage accuracy. Automatic particle counters. These instruments make particle size measurement faster, more accurate, and less prone to human error. Perfect for today's high-tech pharmaceutical labs. There are three main types. First, the Coulter counter, which works on the principle of electric resistance. As each particle passes through a small aperture filled with an electrolyte, it disrupts the current, creating a tiny pulse. Each pulse corresponds to a single particle, and the pulse height tells us its size. Next, the HIAC, or Royco instrument, based on light blockage. Here, a beam of light passes through a fluid stream, and when a particle crosses that beam, it blocks the light momentarily, creating a shadow detected by sensors. The bigger the shadow, the larger the particle. Lastly, the Gell-Mann counter, which uses the Faraday-Tyndall effect, scattering light to count and size very fine particles in suspension. Porosity tells us how much space exists between the solid particles in a powder bed or tablet. It may sound simple, pero napakahalaga nito sa pharmacy kasi these tiny spaces affect how a material flows, compresses, absorbs, and dissolves. Porosity depends on several factors. First, the size of the particles. Smaller particles can pack tightly, leaving less space. Second, the shape of the particles. Irregular shapes don't fit together perfectly, creating more voids. And third, the sorting or arrangement of particles. Uniform particles form consistent spaces, while mixed sizes fill gaps more efficiently. In pharmaceutical manufacturing, porosity affects tablet hardness, disintegration time, and dissolution rate. If the tablet is too porous, it may break easily. If it's too dense, the drug might dissolve too slowly. Now let's take a closer look at intraparticle versus interparticle porosity. Porosity, as we discussed earlier, is the amount of empty space in a powder system. But now, we'll see where those spaces actually exist. Interparticle porosity refers to the large pores between particles. Imagine a pile of marbles. The gaps between them represent interparticle spaces. These spaces affect powder flow and packing, so they're very important in tablet compression and capsule filling. On the other hand, intraparticle porosity refers to the tiny pores within each particle itself. Think of them as microscopic holes inside the particle. They influence absorption, wetting, and dissolution rate. We can calculate total porosity using this equation. Porosity equals 1 minus bulk density over particle density. That ratio gives a decimal value, for example 0.41, which we multiply by 100 to get 41% porosity. In simpler terms, higher porosity means more spaces for air or liquid to enter. Great for fast disintegration, but risky if the tablet becomes too fragile. Let's talk about the types of volume, a key concept in Micromeritics that helps us understand how powders behave during formulation and compression. We actually deal with three main types of volume. First, the true volume, also called particle volume, symbolized as Vp. This is the volume of the solid particle itself. No air spaces, no pores, just the actual matter. It represents the real density of the material. Second, the granular volume, or Vg. This includes not only the solid particle but also the intraparticle pores, those tiny holes found within each particle. So imagine the particle is like a sponge. The spaces inside are counted here. And finally, the bulk volume, or Vb. This one includes everything: the particle, the internal pores, and the interparticle spaces between particles. That's why when you pour powder into a container, the total space it occupies, including air gaps, represents its bulk volume. In simple terms, true volume equals the solid, granular volume equals solid plus inside pores, and bulk volume equals solid plus inside and outside pores. Understanding this helps pharmacists control powder flow, packing, and tablet compression, ensuring every dose is uniform and effective.
Fluidity refers to how easily a powder can flow. In tablet manufacturing, powders must move freely through the hopper into the die cavity and be filled evenly. Otherwise, some tablets end up underweight or overweight. So if the powder doesn't flow well, expect variation in tablet weight, content, and even disintegration time. Compressibility, on the other hand, describes how well the powder can be compacted into a solid tablet without breaking or capping. A powder with good compressibility forms a strong tablet, one that doesn't crumble yet still dissolves properly once swallowed. These two, fluidity and compressibility, are what make granulation so important. It improves both. It turns poor flowing, low compressibility powders into smooth, uniform, and strong granules ready for tableting. One of the simplest yet most powerful ways to measure powder flow, the angle of repose. When you let a powder flow through a funnel, it forms a cone-shaped pile. The angle formed between the surface of that pile and the flat base is called the angle of repose. It tells us how easily or how poorly a powder can flow. If the angle is small, that means the powder spreads out smoothly. Excellent flowability. But if the angle is large, the pile becomes steep, meaning the particles resist movement, showing poor flow due to higher interparticle friction. In the lab, we measure this using the fixed funnel method. We allow the powder to pass through a funnel of known height, let it form a pile, then measure the height and radius of the cone. Using simple trigonometry, tangent theta equals height over radius. We calculate the angle. In pharmacy, this test is crucial because good flow means smooth tablet compression, uniform filling, and consistent dosage, while poor flow can lead to weight variation, segregation, and product defects. Alam nyo ba, class, minsan sa simpleng pagbuhos ng pulbos, makikita mo na agad kung gaano kaimportante ang science sa bawat butil nito. When we talk about the angle of repose, we're actually measuring how well a powder can flow. In other words, gaano kadaling dumaloy o kumalat ang powder kapag ibinuhos. Technically, the angle of repose, theta, is determined using the formula theta equals tan inverse of h over r, where h is the height of the pile and r is the radius of the base. In the lab, we let the powder fall gently through a funnel, forming a cone-shaped pile. The steeper the angle, the poorer the flow. Pero kung mababa ang angle, ibig sabihin maganda ang fluidity ng powder. Perfect for granulation and tablet manufacturing. Let's talk about compressibility, a key indicator of how well a powder can be packed or compressed, and one of the most practical flow tests in Micromeritics. We measure it using the car's compressibility index. Here's how it works. A known mass of powder is placed inside a graduated cylinder, then it's tapped repeatedly, usually by a tapping machine, until the powder settles and the volume stops decreasing. We then measure two volumes, the bulk volume, which is the original loose state, and the tap volume, which is the compacted state after tapping. Car's index is calculated using this formula: tap density minus bulk density, divided by tap density, then multiplied by 100. A low Car's index, around 5 to 15%, means the powder flows easily and packs uniformly. But a high Car's index, say above 25%, indicates poor flow and high cohesiveness. In pharmaceutical manufacturing, this helps us predict whether a powder will flow smoothly into dyes and capsules, or if it will cause weight variation, clogging, or uneven tablet compression. So in short, Car's index tells us how behaved or stubborn our powder is during production. Sa paggawa ng tablet, hindi lang mahalaga na dumadaloy ang powder, kailangan din itong madaling makompress. That's what we call compressibility, the ability of a powder to decrease in volume when pressure is applied. In simple terms, how well can a powder form a strong tablet without breaking apart? In the lab, we measure this property using two important formulas, Car's index and Hausner's ratio. Car's index, or CI, is calculated as CI equals VO minus VF over VO times 100%, where VO is the initial volume and VF is the final tap volume. Meanwhile, Hausner's ratio, or HR, is simply VO divided by VF. If the Car's index is low and the Hausner's ratio is close to 1, that means the powder has excellent flow and compressibility. But if the values are high, the powder is too cohesive. Mahirap i-compress, mahirap i-tablet. Kaya kapag nag-formulate ka, tandaan mo, the numbers tell the story. Behind every perfect tablet lies the balance between flow and compression. Now that we've learned about Car's compressibility index, let's connect it with another important flow parameter, the Hausner ratio. Both of these help us evaluate how easily a powder can flow or be packed during processing. The Hausner ratio is simply the tappet density divided by the bulk density. When the value is close to 1, it means the powder has excellent flow ability. Particles slide smoothly with little friction, but as the ratio increases, say above 1.25 or 1.30, the flow becomes poor, meaning the particles tend to stick together or resist movement. This table shows the relationship between Carr's index and Hausner ratio. If Carr's index is below 10% and Hausner ratio is around 1.00 to 1.11, the flow is excellent. But if Carr's index exceeds 30% or Hausner ratio goes above 1.45, that powder is very poor or cohesive. In pharmaceutical manufacturing, these two values guide us in adjusting formulations, maybe adding glidants like talc or colloidal silica to improve flow before compression or encapsulation. So remember, Carr's index and Hausner ratio are like powder behavior reports. They tell us whether the powder is calm, cooperative, or completely stubborn during tablet making. Now, our next topic is phase equilibria. The triple point. This is the unique temperature and pressure at which a substance's solid, liquid, and gas phases all exist together in perfect equilibrium. Meaning, at this exact condition, the material can simultaneously melt, evaporate, and freeze, all at once. For example, the triple point of water occurs at 0.01 degrees Celsius and 611.73 pascals. At that point, ice, liquid water, and water vapor all coexist, none of them dominating the other. In the graph, you can see where the three curves meet. That's the triple point. Each line represents a boundary between phases, and the intersection marks the only condition where all three states are stable. In pharmacy and formulation science, this concept matters especially when dealing with lyophilization or freeze-drying. We rely on knowing the triple point to prevent unwanted melting or sublimation during processing. So in simple terms, the triple point is nature's perfect balance, where matter doesn't have to choose whether to be solid, liquid, or gas. It becomes all three at once.
Now, let's talk about the critical point. If you look at the phase diagram, makikita mo yung point sa dulo ng liquid vapor curve. That's the critical point. At this temperature and pressure, the liquid and gas phases become identical. They have the same density, so you can no longer tell where the liquid ends and the vapor begins. Beyond this point, we enter what's called the supercritical region, forming a supercritical fluid. This is a very interesting state. It behaves like a gas in terms of flow, but has liquid-like density, kaya it can dissolve materials very efficiently. In pharmaceutical applications, this concept is used in supercritical fluid extraction. For example, extracting caffeine from coffee or purifying heat-sensitive drugs without degrading them. So to summarize, the triple point is where all three phases coexist, while the critical point is where liquid and gas merge into one continuous phase. It's like the substance has transcended its boundaries. No longer liquid, no longer gas, just one powerful supercritical state.
Let's take a closer look at the critical temperature and critical pressure, the two key values that define the critical point of any substance. The critical temperature is the highest temperature at which a gas can still be liquefied kahit gaano pa kataas ang pressure mo. Once you go beyond this temperature, you can never turn it into liquid again. It will remain in a gaseous or supercritical state. Meanwhile, the critical pressure is the minimum pressure required to liquefy a gas at its critical temperature. So in simpler terms, pressure lets you compress it, while temperature sets the upper limit for liquefaction. If we look at the table, notice how water, H2O, has a very high critical temperature, 647 Kelvin, meaning it needs extreme heat to reach that limit. Compare that to carbon dioxide, CO2, its critical temperature is around 304 Kelvin, which is much lower. In pharmaceutical applications, understanding these values is vital in supercritical fluid extraction or drying processes, especially when we manipulate temperature and pressure to control phase changes. Let's talk about latent heat, also known as molar heat. This is the amount of heat required for 1 mole of a substance, whether solid, liquid, or gas, to change from one phase to another without changing its temperature. Halimbawa, when ice melts into water or when water boils into vapor, the temperature stays constant but energy is still being absorbed. That hidden energy is what we call latent heat. Latent kasi hindi mo siya nakikita sa thermometer, pero ginagamit siya to break or form molecular bonds. When heat is gained, we have processes like melting and vaporization. When heat is lost, we see freezing and condensation. In the graph, notice the flat lines. Those are the phase transition regions where temperature stops rising even if heat continues to be added. Without latent heat, no phase change can occur. That's why in pharmacy, during drying, crystallization or lyophilization, controlling heat flow is crucial because latent heat determines how materials change state without decomposition. So remember, temperature measures motion, but latent heat measures transformation. Now let's go deeper into latent heat, this time focusing on heat of fusion, vaporization, and sublimation. The heat of fusion is the heat absorbed or released when a substance changes between solid and liquid. For example, when ice melts into water or when water freezes into ice. During this stage, the temperature stays constant, but molecular bonds are breaking or forming beneath the surface. Next, the heat of vaporization. This is the energy required to change a liquid into vapor. Think of it as the extra energy molecules need to completely break free from the liquid surface, just like when boiling water becomes steam. And finally, the heat of sublimation. This one's special. It's the heat needed for a solid to turn directly into gas, skipping the liquid phase entirely. Like when dry ice, solid CO2, turns straight into vapor. Notice in the graph, the flat lines show where temperature stays steady. That's the power of latent heat. Energy is being absorbed or released, but it's all used for changing the phase, not raising the temperature. In pharmacy, this principle is crucial during lyophilization or freeze-drying, where we remove moisture from drugs using sublimation under controlled pressure and temperature. Let's talk about Gibbs phase rule, a fundamental concept in thermodynamics that helps us understand how different phases of matter can coexist in equilibrium. This rule, proposed by Josiah Willard Gibbs in 1875, tells us how many variables, like temperature, pressure, or concentration, we can change without disturbing the balance between different phases. Mathematically, it's expressed as P plus F equals C plus 2. Here, P is the number of phases present, C is the number of components in the system, and F is the degrees of freedom, or simply the number of independent conditions we can adjust. So for example, in a simple water system, we have 3 phases: solid, liquid, and vapor. When all coexist at equilibrium, like at the triple point, the system's degrees of freedom drop to 0. It's fixed. Temperature and pressure can't change without shifting the phase balance. In pharmacy, understanding phase equilibria helps in formulation stability, crystallization control, and even drug polymorphism studies. The eutectic point. In simple terms, this is the lowest possible temperature at which a mixture of 2 solids, let's say solid A and solid B, can melt together into a liquid. At this specific composition and temperature, 3 phases coexist in equilibrium: solid A, solid B, and the liquid phase. On the diagram, you can see that as we move from A to B, each component has its own melting point. But the line dips down to this one special point. That's our eutectic point. At this point, both solids melt at the same time, giving the mixture a sharp melting behavior, similar to that of a pure substance. In pharmacy, this principle is very useful, especially in formulation design. Eutectic mixtures are often seen in ointments, suppositories, and powders, where combining two components lowers the melting point, improving solubility or absorption. A classic example, camphor and menthol. When mixed, they form a liquid at room temperature because of this eutectic interaction.
Our last topic is chemical kinetics.
Now we move on to chemical kinetics, one of the most important topics in physical pharmacy. In simple terms, chemical kinetics is the study of how fast a reaction occurs and how it happens. It focuses on the rate of reaction, how quickly reactants are converted into products, and the mechanism or the step-by-step pathway that the molecules follow during this process. If you look at the graph, you'll see that as time goes by, the concentration of reactants decreases while the concentration of products increases. The slope of this curve, represented as dc over dt, tells us the rate, how fast this change is happening. In pharmacy, understanding kinetics is essential because the same principles control how drugs degrade, how long they stay stable, and even how fast they're absorbed or released inside the body. That's why kinetic studies are at the heart of stability testing, shelf life determination, and bioavailability studies of pharmaceutical products. So remember, chemical kinetics is not just about speed. It's about predicting and controlling reactions to ensure the safety and effectiveness of every medicine we make. Let's talk about the rate of reaction, also known as the degradation rate in pharmacy. This refers to the velocity or speed with which a chemical reaction takes place, or in simpler terms, how fast reactants are converted into products. In the context of pharmaceuticals, this usually means how fast a drug degrades over time, which directly affects its stability, potency, and shelf life. The rate of reaction depends on several factors. Una, reactant concentration. The more concentrated the reactants, the faster they collide and react. Second, temperature. As temperature increases, molecules move faster, leading to a higher rate of reaction. Third, pH, which can either stabilize or destabilize certain compounds. And lastly, the presence of solvents or additives, which can either speed up or slow down the degradation process. If you look at the graph, you'll notice that higher temperatures generally lead to faster degradation. That's why we perform accelerated stability studies at 30 degrees Celsius or 40 degrees Celsius to predict how a product behaves over time. In short, controlling the rate of reaction means controlling drug stability and product quality. Now let's talk about the order of reaction. When we say order, we're simply describing how the concentration of a reactant affects the rate of a chemical reaction. In other words, how sensitive the reaction rate is to changes in the amount of reactant or drug present. For example, in a zero-order reaction, the rate is constant. It does not depend on how much reactant you have. Kahit madami o kaunti ang concentration, the reaction proceeds at the same speed. A perfect example in pharmacy is the degradation of certain drugs in suspension, where the rate remains constant until most of the drug is gone. Meanwhile, in a first-order reaction, the rate depends directly on the concentration. The higher the concentration, the faster the reaction. This is very common in drug degradation, in solution, and in drug elimination from the body. On the graph shown, we see that as time increases, the concentration of the reactant decreases linearly, and the slope of this line, represented by K, is the rate constant. So to summarize, the order of reaction helps us predict how long a drug remains stable and how it behaves kinetically once formulated or administered.
Now let's take a closer look at the integrated rate law, which connects the concentration of a reactant with time for different reaction orders. Let's start with the zero-order reaction.
Here, the rate of reaction is constant. It does not depend on how much reactant is left. The equation is rate equals K, and when you plot concentration versus time, you get a straight line with a negative slope equal to negative K. This means the reactant decreases at a uniform rate over time. Very typical for suspensions and photolabile drugs. Next is the first order reaction. In this case, the rate is directly proportional to the concentration. Rate equals K times open bracket, A close bracket. The plot of the natural logarithm of A versus time gives a straight line with slope negative K. This is common for solutions and drug degradation, where the reaction slows down as concentration decreases. And lastly, the second order reaction. Here, the rate depends on the square of the concentration. Rate equals K times A squared. The plot of 1 over A versus time gives a positive slope equal to plus K. So, by looking at the shape and slope of the curve, we can tell what order of reaction a drug follows, which is crucial in predicting its stability, shelf life, and expiration period. Now let's learn how to determine the order of a reaction just by looking at the concentration time graph. Let's start with the zero order reaction. In a zero order process, the concentration of the reactant decreases linearly with time. You'll notice the graph forms a straight downward sloping line. The rate constant K is simply the negative slope of that line. Here, the rate of reaction is independent of concentration, meaning it stays constant until the reactant is used up. Next, we have the first order reaction. This one shows an exponential decay curve. Notice that the half-life, or T1 half, remains constant, meaning it takes the same amount of time for the concentration to drop by half, no matter where you start. This is common in drug degradation and elimination kinetics, like how many drugs follow first-order metabolism in the body. And finally, the second-order reaction. The curve here drops more sharply at first, then flattens out slowly. The key difference? The half-life is not constant. As concentration decreases, it takes longer and longer for the next half to disappear. So in summary, straight line, zero order. Constant half-life, first order. Changing half-life, second order. These patterns help pharmacists and formulators predict drug stability, shelf life, and reaction behavior in real-world conditions. Now let's talk about the zero-order reaction. In this type of reaction, the drug concentration changes at a constant rate over time, meaning kahit gaano pa karami o kakaunti ang reactant or drug present, the reaction proceeds at the same speed, steady, predictable, and independent of concentration. If you look at the graph, the line goes down straight and linear, showing that the concentration of the reactant decreases uniformly as time passes. The slope of that line represents the rate constant K, and it's negative since the concentration is going down. A perfect real-world example, drug degradation in suspension form. Here, the breakdown of the active ingredient happens at a constant rate, kaya ang amount of drug loss per hour or per day is always the same until it's almost gone. So to summarize, in zero-order kinetics, the rate is constant, the plot is linear, and the reaction speed does not depend on concentration. Now let's move on to the first-order reaction. In this type of reaction, the rate depends on the concentration of the drug remaining. So habang nababawasan ang drug concentration, bumabagal din ang reaction rate. It's directly proportional. When the concentration is high, the rate is fast. When the concentration drops, the rate slows down. If you look at the graph, you'll notice it still forms a straight line, but only when we plot the natural log of concentration versus time. Here, the slope of the line is negative K, which represents the rate constant. This type of reaction is actually the most common in pharmacy. Most drugs degrade or metabolize following first-order kinetics. For example, in pharmacokinetics, drug elimination from the body often follows this pattern, meaning a constant fraction of the drug is eliminated per unit time, not a constant amount. So to summarize, in a first-order reaction, the rate depends on how much drug is left. The natural logarithm of A versus time plot is linear, and the slope equals negative k. Now let's compare how zero-order, first-order, and second-order reactions behave in terms of rate and concentration over time. Let's start with the top graphs, rate versus concentration. For a zero-order reaction, the rate is constant. See that flat line? It means the reaction rate doesn't depend on concentration. Kahit magbago pa ang amount of reactant, tuloy-tuloy lang sa parehong bilis. Next, in a first-order reaction, the rate increases linearly with concentration. Double the concentration, double the rate, proportional sila. Then, for the second-order reaction, the rate shoots up exponentially. It's not just proportional, it's squared. So a small increase in concentration can cause a much faster reaction. Now look at the bottom set, concentration versus time. For zero order, the plot is a straight line going down. Linear decay. For first order, it curves downward smoothly, exponential decay. And for second order, it drops sharply at first, then flattens slowly, a more pronounced curve. So in summary, flat rate, zero order, straight rate line, first order, curved and steep, second order. These visual patterns help us identify the reaction order just by observing how rate and concentration change over time.
Now let's talk about half-life, or what we call the one-half. Half-life is the period of time required for the amount or concentration of a drug in the body to decrease by one-half, or 50%. In simple terms, it's how long it takes for half of the drug to disappear from your bloodstream. Look at the curve on the right. This represents the pharmacokinetic profile of a drug. After administration, the concentration rises during the absorption phase until it reaches its peak. That's the Cmax, the highest concentration of the drug in the blood. Then comes the elimination phase, where the curve starts to fall. At the halfway point of this decline, we mark the T1/2, or the half-life, the exact time when the drug has lost half of its maximum concentration. The AUC, or area under the curve, shows the total drug exposure. How much of the drug was present in the body over time. Pharmacists use half-life to determine dosing intervals. How often a patient needs to take the medicine to keep drug levels effective without causing toxicity. So remember, half-life determines how long a drug stays active. Too short means frequent dosing. Too long means possible accumulation. Now let's talk about shelf life, symbolized as T sub 90 or T90. Shelf life is the period of time during which a drug product retains at least 90% of its original concentration, meaning only 10% has already degraded. In simple terms, kapag sinabi nating T90, ito yung time kung kailan ang gamot ay nasa 70% potency pa, safe pa siyang gamitin, and still within specification. Beyond that point, the drug may start to lose its effectiveness or stability. If you look at the image, the expiration date printed on the label is based on this concept. That's the manufacturer's assurance that the product, when properly stored, will still meet its quality, purity, and potency until that date. In pharmaceutical formulation and stability studies, determining T90 is crucial. It tells us how long a product can stay effective under normal storage conditions. So remember, half-life describes drug elimination in the body, while shelf life refers to drug stability on the shelf. Both are about time and degradation, but one protects the patient and the other protects the product. Now let's look at how shelf life, or T90, is actually determined in real stability studies. On this graph, the red dots represent the testing results. These are the actual measured potencies of the drug product over time.
Notice how they slowly decrease. This shows degradation happening naturally as the product ages. The red line in the middle is the estimated degradation line. This predicts the trend of potency loss through regression analysis. The black boundary lines are called the 95% confidence limits, meaning we are 95% sure that the real values of degradation will fall within this range. When the degradation line drops to 0.90 or 90% of the initial concentration, that point on the x-axis, measured in days, becomes the shelf life, T90, of the product. So in essence, this graph translates laboratory data into real-world assurance, showing how long the drug remains stable, potent, and safe for patients. That's why in pharmaceutical quality assurance, we don't guess expiration dates. We calculate them based on science, statistics, and stability data. Wow! Congratulations everyone! You've just completed our physical pharmacy lecture series. Take a moment to appreciate that, because what you've learned here is more than equations and graphs. You now understand how drugs behave, how they transform, and how we as pharmacists ensure their quality, safety, and stability from the laboratory all the way to the patient. Remember, every reaction, every curve, every concept you studied connects to real lives. The next time you see a medicine label or calculate shelf life, think about the science and integrity behind it. I'm so proud of your effort and dedication. Kahit mahirap, you kept learning, kept asking, and kept growing. So again, congratulations future pharmacists. Keep the passion burning, stay curious, and never forget, science is your service to humanity. Thank you so much, and see you in our next class.